In this particular case, slide right here, we have a primary datum feature referenced MMB, okay, but we only have size, okay. In the last example, we talked about, when we used this, we used a virtual condition, okay, because virtual condition took into account the maximum material condition here plus the tolerance of this form. In this case, we don't have that. We have no form tolerance. We just have this size tolerance. And we're referencing this feature control frame for this positional tolerance at the maximum material boundary, in which case the maximum material boundary equals the MMC condition because there are no form tolerances. Okay. Now, a little subtle variation here is that I have the same feature, but I have a form tolerance applied. In which case, my MMB, my maximum material boundary, becomes the MMC of the shaft plus the straightness tolerance. So it's a slight difference between these two interpretations. Okay, in this case, we don't have a form tolerance. And so our MMB actually equals the MMC. In this case, we have a form tolerance applied to our shaft, in which case the MMB is going to equal the virtual condition of the shaft. So it's a slight variation. Okay, we got a tertiary datum feature referenced maximum material boundary. Okay, that's this datum C over here. So we have this location of these holes here, and they apply to datum B and also to datum C, regardless of material boundary. Okay. Applicable MMB determined using the tolerance applied relative to the higher order of precedent datums. So it may include size, form, orientation, or position tolerances. Okay, so let's talk a little bit more about modifiers on datum feature references. So when we use an MMB modifier, it increases the allowable variation and can reduce the detail cost of the part. However, we need to be careful here because it may adversely affect the function due to additional tolerance variation. Now, least material boundary also allows for additional variation. Now, we don't talk too much about least material boundary or least material condition, but essentially when we use those, we're more concerned about, not necessarily concerned about what position of the hole is or part fit or stuff like that. When we're using least material boundaries or LMC conditions modifiers in our feature control frame, we're typically worried about things like wall thickness. I mean, can this section get so thin that it's going to cause us problems? Okay, so wall thickness is protected, but worst condition wall thickness is permitted to occur at all sizes of the relative features. So what we're doing with a least material boundary or least material condition, the typical application for that is protecting the thickness of an edge distance. The regardless material boundary eliminates any additional tolerance based on boundary departures. It reduces variations, but it can increase cost and complexity. When I was talking about this example right here, where we had this part using a MMB modifier, and we managed to put our simulator out there with this plug made to the virtual condition of the axis. So yeah, that was a lot easier to accomplish than, once we made this thing RMB, we made that regardless of material boundary. I got to make a fancy tool fixture over here that not only has to put the plug under, I have to manipulate this plug to expand in this tolerance and pick up B regardless of feature size. Yeah, it's a whole different ball game. It gives you a much tighter precision on your parts. But it can drive up costs. That's why we only use these when you really need it for the function of your part. So that's what I wanted to say about these further considerations of modifiers and datum features. So RMB eliminates all additional tolerances, but it can drive up costs. And so just use that sparingly only if you have to. is what it is. So here, let's talk about datum targets based on order of precedence. Consider datum precedence when defining datum targets. Okay, what this comes down to is that, for datum A, which is going to be our primary datum, we're going to need three targets. 1, 2, 3, because 3 points define a plane. And then when it comes to datum B, we're going to need two targets, datum B, because that's our secondary datum. So for our tertiary datum, datum C, hey, we only need one. Okay, so we need to consider our datum precedence when defining datum targets on a drawing. Identify datum features on a given part because cast surfaces are too uneven for use as datum. So we use these datum target points a lot on cast parts, because as parting lines and irregular surfaces and stuff like that. And what we have to do is have the machining features internal to these cast parts be in the proper orientation. So we set up target points on the outside surfaces of the cast parts. And this is kind of like how we would do that with datum targets. Now let's talk about compound. Your book also uses the word common, but in a compound datum feature, we're using two or more features used simultaneously to establish one datum. So datum feature reference shows letters separated by a dash within one compartment. So, okay, one compartment here. It's B to C. B at MMB and C at MMB. Okay, so what we have here is we have datum A, and then we have datum B and datum C. Okay, so datum features of equal precedence, and it's applicable to cylindrical, flat, and other shapes. Okay, so what we're doing here is we're establishing these two datums to establish an axis between the part. And then we're going to use that to check our profile of this surface right here. Okay, so our datum reference frame is we're going to arrest degrees of freedom by picking up both of these two datums. Okay, and your book also calls it common datum features, but this is compound. In a compound datum feature, we're using two datums to establish essentially one datum, and we do that by placing a dash between the two datums, and we put them in the same datum reference block here. This is also common for cylindrical parts. Okay, in which case here we have this part. It has two centers on it, datum A on one end, datum B on the other end. These two are features of size. And how would we simulate that? Okay, we would simulate that with a V block, two identical V blocks that pick up these two datum axes of the part. And we use that, we could spin the part around, and so we can measure our runout of this conical surface, or the runout of this surface, or the runout of this flat surface right here. Okay, so that's how we would use a compound datum feature. Again, we're not using material modifiers here in this case. We got A dash B within a single block of the feature control frame. Okay, so using real features as datum features. Okay, I want to bring this up again because again it's really important. Datum features are physical features on a part. Do not place datum feature symbols on a center line. Okay, you're just lining up these center lines. What we would do is we would put the datum feature on a surface and define a basic dimension from that surface relative to position of these holes, and then we would establish a geometric tolerance for the position of these holes relative to that datum. We do not put datum features have to be touched. We do not put datums on center lines, okay, because we could produce these holes off and not even really know it. So we cannot put datums on center lines. We need to use surfaces and then basic dimensions to establish the location of those holes back to the datums. So I can't talk about that one enough. Let's talk about step datum surfaces. In this case, we're creating a datum A using these two sets of targets, but there is a step between those two. So this basic dimension defines the datum step. So we got these two or more non-coplanar surfaces being used to establish a datum, and that's how we do it. We do it with a basic dimension, and we do it with an offset step. Equalizing datum targets. Now, this causes the piece to be centered. Okay, so these symbols here, that's equalizing. Okay, so it allows us to give us a movable datum target symbol indicated. So the direction of the movement is indicated with line if needed. So in this case, let's look at what this simulator looks like. We have these knife edges back here that make contact with this larger radius, and then we have a movable item here in our simulator that allows us to pick up these two datum points regardless of the size of this. So this is called an equalizing datum target. This concludes the movies for Lesson 6 or Chapter 6. Thank you.